I'm going to put up another homework, I think tonight. I forget depending on what the problems are, will depend on what the due date is. Yes, Ricardo.
If I submit the homework at 11:59 tonight, am I fine?
Yeah. Yeah. Yeah, the deadlines for homework in this course, it's sort of an open secret, are not as rigid as they were in 2200, okay? But I don't want that to become a habit for people, because the graders have lives, you know, and they can't be getting homework really late. But what's going to happen is I'm going to send you an email that says, I'm about to put up solutions to homework 1. Is there anybody out there who still hasn't handed in homework 1 and wants to? You know, that kind of thing. And when that happens, you know, we need to get it done. And part of the reason for this is I want everyone to do the homework. I want that to be, I want it to be something you want to do and that's not an unpleasant experience. So I told the graders not to do, you know, sort of a rigid smackdown style grading. B, I don't want it to happen so that when it gets to be like 5 p.m. on a certain day, you say, oh, I missed, I'm not going to do it, I'll just wait for the solutions, because that's not a good way to learn the material, you know. Everything looks so nice in the solution. Oh, yeah, right, okay, that's easy, yeah. And then, you know, try it on the test, haha, you know, that's whatever. You hear me? Yes, Maroon.
Out of curiosity, but relatively speaking, how much later than the soft deadline do you expect your solutions to go up?
Well, the solutions have a mind of their own, and when they tell me they want to go out, they... No, actually, yeah, it varies a lot. Like, for example, when we get close to a prelim, it's going to be like, guys, this homework's on the prelim, I have to put up solutions. So, you know, come on, you know, whereas, whatever. You know how it is. Try to do it by the date I ask you to try to do it by, okay? Fair enough? All right. Any other questions before we move ahead? Did everyone have fun at the career fair yesterday? Yeah? It was, oh, I bet it was hot. Yeah. And did anyone besides Manish meet the guys from APT, Applied Predictive Technologies? No? Good, because both of them took 3250, and one of them was actually a TA for it when the other one took it. So that's kind of... How about Google? Did you talk to the Google guys? Well, Matt and Toshi both took class, or Matt didn't take classes from me, but Toshi took my NGRI, and Matt grew up in my hometown, right around the corner from where my parents lived, so it was kind of interesting. Yeah, I kept running into people last couple days. And Cameron even came to class that one on Tuesday. That was pretty cool. But anyway, we started talking about discrete time signals and stuff you could do with them. And remember the definition of a discrete time signal. It's just a mapping. X that takes the integers, and the integers are our model for discrete time, into either the real or complex numbers. And I'm using this notation, Blackboard bold F, to denote real or complex numbers, as I was before. So that's what a discrete time signal is. And F to the Z is the notation we're using for the set of all such things and last time we noted that F to the Z has a natural vector space structure. So what was that? What is a vector space? A vector space is just a set on which you have a notion of taking linear combinations and that everything works the right way with respect to 0. So the quote-unquote 0 vector is the 0 signal, and the 0 signal is just the signal x, whose specification is x of n equals 0 for all n. And if you're given x1 and x2 in F to the Z, and constants C1, C2 in F, you can form a signal x equals C1x1 plus C2x2. And remember, we're going to be using just the letter for the signal to describe the whole signal. And we're never going to put of n or anything unless we're talking about its value at a specific time. And you'll see more of that as we go along today. So this is the signal with specification x1 of n, or x of n, is equal to C1 x1 of n plus C2 x2 of n for all n in the time set z. And we introduce two special signals: the discrete time unit impulse, delta, and that has specification whoops, wrong one. Delta of n is equal to 1 when n is equal to 0, and 0 when n is not equal to 0. And the discrete time unit step, u. And the difference here again from 2200 is we're talking about u and delta, not u of n and delta of n. Okay, we're beyond that now. So this one has specification u of n is equal to 1 when n is non-negative, and 0 when n is negative. Okay, so that's about where we were last time. And today what I want to do is I want to talk about properties that discrete time signals may or may not have. Some of these are algebraic properties, some of them are analytical properties, and when we talk about the analytical ones, we're going to learn some notation that's going to play a major role later on in the class. And it's pretty high-level notation and pretty high-level concepts for a course generally at the junior level. But that's the freedom we have based on having had 2200. We can talk about things like this. So anyway, so here's some properties that a signal. Oh, actually, before I do those, I want to talk about one other thing you can do to signals. Okay. So here's a key operation you can perform on signals, and that's time shifting. And we see this a lot. Like when we're trying to figure out whether, say, a system is linear and time invariant, we need to shift things and see what happens. So how does this go? Given a discrete time signal x, so given an x in f to the z, and some integer k0, define shift sub k0 of x as the signal with specification what? And here's where we're going to, well, you'll see. Shift k0 of x evaluated at any time n is equal to x evaluated at n minus k0. And that's true for all n in the integers. Now that left-hand side is kind of a mess of parentheses and stuff. So let me just be really pedantic and specific. What is this part of it? This shift k0 of x, that's the whole signal. Whereas shift k0 of x at n is its value at time n. So when I talk about shift k0 of x, when x is a signal, I mean a whole signal. I'm talking about a whole range of values. When we talk about shift k0 of x at some specific n, we're talking about a specific value of that whole range of values. And we're going to see this kind of thing coming up quite often. Now, there's something cool about this operation, shift k0. You can view it as an operation that takes something in f to the z to something in f to the z. So note, for each k0, shift k0 is a mapping that takes f to the z to f to the z. So we can think of it as a mapping on a whole function space. And it's a certain kind of mapping. I'm going to leave a blank there. So it's a mapping from f to the z to f to the z. Now, what kind of mapping is it, do you think? Given we know that f to the z has some structure, right? It has the structure of a vector space, right? What kind of mappings on vector spaces are interesting from a mathematical standpoint? Zach? Bijective. It is bijective. Okay. That's a fact about it, for sure. But and I'll mention that after this, but the key thing about it has to do with the fact that f to the z is a vector space, and certain mappings from vector spaces to vector spaces are of special interest. Manish. It's that too, and that actually is almost the same thing as saying it's bijective. It's simpler than this, guys. Well, in a way. Come on. Somebody must have a... Who said that? Yeah. Okay, what's your name? Rohit. Rohit? Okay, I should know you from before. Yeah. It is a linear mapping from f to the z to f to the z. And also bijective, but whatever. Okay, I'm not dismissing that as an important thing, but what is a linear mapping on a vector space? This is something we encounter time and time again. That is to say, if x1 and x2 are in f to the z, and c1, c2 are in f, then if I take shift k0 of c1 x1 plus c2 x2, what I get is c1 shift k0 of x1 plus c2 shift k0 of x2. That's what it means for a mapping on a vector space to be linear. That if you take the mapping and you operate on a linear combo of two things, you get the same linear combo of the mapping operating on the individual things. And shift k0 is such a mapping, and when we talk about LTI systems, mapping sets of signals into sets of signals, they're going to be such mappings. And that's where the L in LTI comes from, but that's a couple days hence. All right, so that's another nice thing you can do, time shift. Now let's talk about some of those properties of signals that they may or may not have. First, some sort of structural algebraic properties. So here's some properties a signal may or may not have. All right, first one. We say that x in f to the z is right-sided when what? When there exists some n1 in the integers z such that x of n is equal to 0 for all n before time n1. That's what a signal being right-sided means. In some sense, it turns on at some specific time. And before that, it's off. And it could stay off forever, like, well, we'll get to that in a few minutes. So that is to say, it's quote unquote off before time n1. And similarly, we say that x in f to the z is left-sided when you can find some n2 such that x of n is 0 for all n bigger than n2. And we say x has finite duration. So the colloquial meaning of right-sided is, that is to say, it's quote-unquote off after time n2. And finally, we say x in f to the z has finite duration when what? What's a fancy way of saying it has finite duration? Yeah, it's both left-sided and right-sided. And in terms of being on and off, that means it's off except for a bounded range of times. n1 less than or equal to n less than or equal to n2 for some n1 and n2. Okay, so a little reality check here. Is the zero signal right-sided? No. Okay, who said no? And tell me why not. No, could be. So what's your rationale for it's not being right-sided? The definition of right and left-sided, by the way, they don't say anything about what they do when they're allowed to be non-zero. It just says that they have to be 0 before some time or have to be 0 after some time. So I'll ask again, how many people, well, let's not do a vote. Is the zero signal right-sided? Yes, it is right-sided, trivially so, because you can just pick an arbitrary n1, and it is 0 before that time n1. Therefore, no matter what it does after time n1, it satisfies the definition, but it happens to be 0 to the right of n1. It's allowed to do that. It's allowed to be 0, even when it's allowed to be non-zero. So zero signal is both right and left-sided and therefore has finite duration. What about delta? What about the discrete time unit impulse? Is that right-sided? Yes. How about left-sided? Yes. And therefore it's finite duration. What about the unit step? Is that right-sided? Remember, right-sided means it's allowed to be zero over there but not over here. So again, is the unit step right-sided? Yes. Is that you? You didn't get. I
guess I didn't get enough sleep.
Didn't get enough sleep? Did you have fun at the career fair?
I guess.
You guess? Okay. Yeah. Okay. The unit step is right-sided. It's off before time zero, right? Or if you wanted to be perverse, you could say it's right-sided because it's off before time minus 19. Right? Doesn't matter when, as long as it's off before some time, then it's right-sided. Is it left-sided? No. No, because it's always on after time zero. It's always 1, 1, 1, 1, 1, and so on, right? So it never turns off. Never turns off means it's not right-sided, and therefore it doesn't have finite duration. Okay, so that's the reality check. Now, suppose someone comes up to you, well, let's not do that. Let me just ask the question point blank. You know what a vector space is. It's a place where you can take linear combinations, right? You know what a subspace of a vector space is? Does everyone remember that? Ricardo? What is it?
It's any linear combination of the space itself.
Okay, that's not, that has part of it in it. Okay, a subspace of a vector space is a subset of the vector space that has a certain property. Dan?
It spans the vector space?
Well, it doesn't have to span the vector space. Yeah, Brian. That's the key point, the second thing, because that actually implies that it has a zero vector. A subspace of a vector space is a subset of the vector space that's closed under taking linear combinations. In other words, if you take any two things in the set and linearly combine them, you get another thing in the set. So let me just remind you of that. Recall, and this is Math 2940, and if you want to review it in EC 3250 language, you can look at the chapters on linear algebra and the monograph that I'm not going to cover in class. Recall that, say, V contained in f to the z is a subspace of f to the z. And sometimes I'm going to underline the space to emphasize the fact that it's not just an arbitrary subset. When V is closed under taking linear combinations. That is to say, when x1 and x2 are in V, and c1 and c2 are in F, we have c1 x1 plus c2 x2 also in V. Taking linear combinations of things in V doesn't take you out of V. That's what it means to be a subspace. And we're going to see a lot of subspaces of f to the z as we go through this stuff. Here's a question. Is the set of all right-sided signals a subspace of f to the z? How many? This is an interesting question. So here's a question. Is the set of all right-sided signals a subspace of f to the z? David? Okay, that's a good try. Might be right. This is a good vote question. This is a good voter question. How many people think that the set of all right-sided signals is a subspace of f to the z? Okay, how many people think it's not a subspace? That's a close vote and many abstentions, as always. Okay, so someone who thinks, I want to hear reasons. Why do you think it's not a subspace of f to the z?
Because it's not closed. Because you can theoretically just keep moving the bound on, like, what makes it right.
You could do that. You could.
There's no, like, end to it.
Yeah, he's saying, let me see if I can summarize what you're saying. That x1 could start some time way long ago compared to x2. And that long ago could be arbitrarily far. That's true, but remember, when we want to figure out whether it's a subspace, all we have to do is consider the following narrow question. If you give me an x1 and an x2, and I take a linear combo of them, is that signal still in the set? Now, someone who thinks it is a subspace, tell me why they think it. Stephen.
You have x1 and x2, and then you find the n1 value for that. Then the least n1 value for those two will still be an n1 value for c1 x1 plus c2 x2.
Yes. You're only considering that narrow question about two specific signals. So there's no chance for one of the n's to go back to negative infinity. Okay? If I have two signals, both of which start at some specific time, they might be different starting times. And I take a linear combo of them, then that linear combo starts at the earlier of those two starting times. Therefore, linear combo of any two right-sided signals is still right-sided, and its starting point, so to speak, is going to be the lower of the two. So yes, even if x1 and x2 have different on times, say, let's call it that, c1 x1 plus c2 x2, will have an on time, namely the earlier of the two. Okay? And similarly, what about the set of all left-sided signals? Is that a subspace? Yeah, because, so similarly, the set of all left-sided signals is a subspace of f to the z, even if you have two signals, even if their off times are different, if you linearly combine them, that linear combo will be off after the later of the two off times. And the set of finite duration signals is also a subspace. It's closed under taking linear combinations. Now, you could take a linear combination of two finite duration signals and get one of longer duration than either of the two. And you could keep linearly combining them with other finite duration signals and get longer and longer duration signals, but anything you get in that process is going to have finite duration after a finite number of steps in that process. All right, that's something cool. So now we know the right-sided signals are subspace, left-sided are subspace, finite duration are subspace. Are these subspaces closed under shifting? What does it mean to be closed under shifting? So question. what does it mean for a subspace to be closed under shifting? Let me just tell you what it means. A subspace V of f to the z is closed under shifting when, for every k0 in z, if x is in V, then so is shift sub k0 of x. If you shift something in V by any amount, then you get another thing in V. That's what it means for V to be closed under shifting. Is the set of all right-sided signals closed under shifting? If I shift a right-sided signal, do I add another right-sided signal? Yeah. It just starts at a different time. How about the set of all left-sided signals? Similarly, if I take a left-sided signal and I shift it, I get another left-sided signal that happens to end at a shifted time. And finite duration. It's pretty clear that if a signal starts here and ends here, and I shift it by a certain amount of time, it's still going to have a starting and ending point. So all these subspaces, so the answer to the question is yes for all. Okay, so all those subspaces are closed under shifting. Great. Those are the quote-unquote algebraic properties of signals that I wanted to talk about. Now I want to talk about some more difficult ones, in my opinion, these analytical properties. Okay, so let's go for that. So now for some important analytical properties that signals may or may not have. Okay, first one. We say that x in f to the z is bounded or is a bounded signal when what is true? When there exists some ceiling and a floor to all the values of x. And a good way to state that is as follows. There exists some positive real number, let's call it r, such that x of n, absolute value or magnitude, depending on whether you're talking about a real or complex signal, is less than or equal to r for all n in the integers. So if you think of the signal x of n, if you say plotted its values all out in a big long row, there would be some roof that you could put over the top of it and some floor that you could put below it that the values never exceeded in either direction. This property is one that people often conflate in their heads with the idea of finite duration. So be careful about that. And on the homework, you'll have plenty of opportunity to conflate those two things. Finite duration is about how long the signal lasts in time. Bounded is about the signal's values. How high and low can they go? So it's like two different notions of finite walls. Like finite duration signal has a wall in time in between which all the action occurs. Bounded means it doesn't have to be finite duration, but the action never goes above a certain point or below a certain point. And bounded signals are obviously really important, right? Here's some notation. And this is something you probably haven't seen before, but it's standard notation. We use this lowercase l superscript infinity to denote the set of all bounded discrete time signals. And the way you pronounce that is L infinity or little l infinity, because we're going to have big L's later on when we talk about continuous time. So the pronunciation here is either little l infinity or just L infinity, depending on the context. And the reason for the little is that we're going to have a big L infinity later on when we talk about continuous time signals. You don't say L to the infinity. You just say L infinity. I mean, people will know you're a total hack if you say L to the infinity. All right. Question. Is L infinity a subspace of f to the z? If I take a linear combo of two signals, each of which is bounded, possibly with different r's, do I get a signal that's bounded?
Yes.
Yes? How come? What is a guesstimate of it, what its bound might be?
The max of, or the sum of one signal plus the sum of the other. Or, yeah. The maximum value you could get from each of them combined together. The larger of the r bound max of r1.
Well, if I take C1 x1 of plus C2 x2, it's going to be absolute value of C1 times R1 plus absolute value of C. Yeah, it turns out it is a subspace. Okay. L infinity is a subspace of f to the z. And is it closed under shifting? If I shift a signal that's always between a ceiling and a floor, do I get another signal that's between the same ceiling and the floor? Yeah. So it's also closed under shifting. Okay, now Ricardo was trying to pull us ahead to this next point here. There's a measure of sort of how big a bounded signal is. And that's called its infinity norm, or its L infinity norm. So here's a measure of quote-unquote size for signals in L infinity. It's called the infinity norm and if I'm given x in L infinity, a bounded signal x, set x infinity, and this, I'm sure you've seen the signs for a norm, like from linear algebra, and you may have sort of a vague idea of what a general norm is on a general vector space. It's something like that measures the size of vectors and that like satisfies the triangle inequality or something like that, right? You saw all that stuff before, right? A little bit. Say yes, please. Yes. Okay. But this is and like the typical one on, you know, Rn is going to be the sum of the squares to the 1/2 of the components, blah, blah, blah. This one is the sup of the set of all absolute value of x events, or magnitudes, such that n is in the integers. The set inside the parentheses there is a bounded set of real numbers, non-negative real numbers, by virtue of the boundedness of the signal x. The sup of that set is a measure of, quote unquote, how big x is. And carrying on, note that if I take C1 x1 plus C2 x2 and take the infinity norm of that, this is going to be less than or equal to absolute value of C1 times the infinity norm of x1 plus absolute value or magnitude of C2 times the infinity norm of x2. And that's for all x1 and x2 in L infinity, and C1, C2 in F. Okay, reality check. Is the zero signal in L infinity? Yes, it is. It's trivially bounded. Or you could say, well, he just said L infinity is a subspace, and every subspace has to have the zero vector, right? So that's a really overly powerful sledgehammery reason why 0 is in L infinity. What about delta? Is delta in L infinity? No. Someone said no. It is. In discrete time, yeah, it is. Because it's equal to 1 or 0. And clearly the set of values there is bounded between the ceiling of 1 and the floor of 0. Is the unit step in L infinity? Is that a bounded signal? Yes. Because it never goes above 1 or below 0. Okay, so that's L infinity. Now we're going to have some other L's, and now's a good time to take a 3-minute break. We'll talk about those other L's in a second.
I made you something.
Suppose x1 and x2 are the same, c1 is 1 and c2 is minus 1. Then that's 0 in there.
Oh, okay.
So for specific choices of c1 and c2,
Okay.
yeah.
I got you.
Yeah. And that's actually not trivial to show what I put up there. But you know.
Number 2, like, if you...
Is that the
It's the relative cardinalities one that I'm trying to show.
power set?
Yeah.
Yeah.
So how would we do that without thinking about the cardinalities at all? So like the thought process I was thinking is that like there's some injective mapping from the power set back to the original set, right? But if you let that injective mapping be that every element of said set that's in the power set gets mapped back onto itself in the regular set, then there has to be at least one more element in the power set that is...
They can't go anywhere. That has to go to the same thing as another one did. That's the point. What you just sort of did was prove that there's no injective mapping.
Right, that's what I meant. It's
yeah.
like a proof by contradiction. But,
yeah, that's fine.
But the issue is that that is using relative cardinalities. Right?
No, it isn't really.
Okay, then I guess that's fine. How would you do it with relative cardinality? If you like actually like used out those like.
I don't think you can. I mean, because the way we've defined relative cardinality is in terms of the existence of certain injective mappings.
Oh, okay.
So
you can't
implicitly, you're kind of using it in the background, but you're not alluding to it.
Okay.
Formally.
All right, that makes sense then.
Yeah.
Yeah, because what I meant was like if you were to use the size of the set as a proxy for cardinality, since they're
For a finite set, you have 2 to the n.
But iterating up through.
Yeah, but for infinite sets,
It doesn't. Yeah, you can't.
yeah, you can't do 2 to the infinity.
Okay. All right. Cool.
Yeah. Okay. So anyway, that's L infinity, set of all bounded things, bounded discrete time signals. And now we have a couple more important L's, not a couple more L's that are important. I don't mean a couple L's that are more important than L infinity. See, you understand my pickiness there, right? Yes, okay. So you got L infinity. And we say that x in f to the z is absolutely summable when, you can probably guess, the sum from n equals minus infinity to infinity, magnitude or absolute value of x of n, is a convergent series. That's what it means for a signal to be absolutely summable. Is the set of absolutely summable signals closed under shifting? What do you think? Is it a subspace? Well, first let's give it a name. So let's denote by little L1, or L1, that's, you pronounce that L1, the set of all these. Is L1 a subspace of f to the z? If I take a linear combination of 2 absolutely summable signals, do I get another absolutely summable signal? How many think, yeah, Jay is emphatically saying yes, so. That might work on my nephew, but I don't. You're close. Yeah. It turns out L1, and it's easy to show. You can just look in the monograph. L1 is a subspace of f to the z. Actually, why don't we just show it? What the heck? No, I don't want to do it. It's just boring. To do it rigorously, you have to say for every capital N, you do the partial sum and it goes out and, whatever. Just don't want to go there. But is it closed under shifting? If I shift a bunch of numbers to the right by some amount, say, and don't mess with their values at all, just shift the whole shebang to the right, is the sum of all their absolute values going to still converge? Yeah, because it's just the same set of absolute values, just in a different place, right? So again, this is a subspace of f to the z, closed under shifting. And we have, just as we had an infinity norm on L infinity, we have a 1 norm on L1. So a notion of size is the so-called 1 norm. And that's just, again, the norm sign around x, but now we have a subscript of a 1 instead of infinity, and this is just the sum from n equals minus infinity to infinity of the magnitude or absolute value of x of n for all x in L1. So that's kind of like how big is an L1 signal is that sum. Observation here. L1 is a subset, in fact a subspace, of L infinity. How come? Why is that true? If I have an infinite array of numbers whose infinite sum is finite, which is the same thing as saying the thing is in L1, does that necessarily have to be a bounded set of numbers? Yes, it does. There's no way if the set of all values of x of n ranges arbitrarily high or arbitrarily low, then that infinite sum is never going to converge. Okay? So if that sum converges, i.e. if x is in L1, then x is bounded, i.e. x is in L infinity. That's another way of saying L1 is a subset of L infinity. So that is to say, if x is in L1, then of necessity x is in L infinity. Okay. And the last L I want to talk about, even though you can do an L for any p between 1 and infinity, is L2. And what's that? Oh, okay, so we've been doing the reality check every time. Is the 0 signal in L1? Yes, obviously. How about delta? Is that in L1? Yeah. What's its 1 norm? What is the 1 norm of delta? This is good. This is good. Yeah, let's figure it out. Let's do it formally, just for the heck thereof. So note, if I take the sum from n equals minus infinity to infinity of the absolute value of delta of n, I get a bunch of zeros plus a 1 plus a bunch more zeros equals 1. Okay? That is to say, delta norm 1 of delta is equal to 1. Okay, so that's an example of a signal that's in L1. What about the unit step? Is that in L1? A good way to check and see is if we can actually compute that sum. So how about you? So in particular, delta is in L1. How about you? So meanwhile, if I try to take the sum from n equals minus infinity to infinity of u of n, absolute value, I get dot 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 plus 0 plus 0 plus 1 plus 1 plus 1 plus 1 plus 1 plus dot dot dot. Doesn't converge. So u is not in L1. And in particular, that demonstrates that the containment here between L1 and L infinity is an improper containment, or is a proper containment. There are things in L infinity that are not in L1, and U is a prime example thereof. All right, good. So far, so good. Finally, L2. What is that? We say a signal in f to the z is square summable when the sum from n equals minus infinity to infinity, guess what? Magnitude squared of x of n is a convergent series. And we denote by L2 the set of all such things. And is it a subspace? It turns out yes. That's not easy, not super easy to show, but where you're going to do it on the homework. So it turns out, see homework, that L2 is a subspace of f to the z. It's closed under linear combinations, and it's also closed under shifting. And we have a notion of size. On L2, and that's the so-called 2 norm. And how is that defined? The 2 norm of a signal x in L2 is the sum from n equals minus infinity to infinity of magnitude of x of n squared to the 1/2. Don't forget the square root. Turns out to be important. Now, if you think about it, this is the natural, like, infinite dimensional generalization of the Euclidean norm on Rn or Cn, right? You saw that when you took Math 2940 probably. Like, if you have a vector, the length of the vector, like an n-dimensional vector, is going to be the sum of the squares of the individual components, magnitudes raised to the 1/2, right? You can think of a discrete time signal as an infinite vector. It's got an infinite number of entries, so to speak. And if you take the sum of the squares of the magnitudes of all those entries and raise it to 1/2, that's like the length of the vector, how big the vector is. So this is an appropriate generalization of the 2 norm on finite dimensional vectors. So note that x2, 2 norm of x, is sort of the infinite dimensional version of, say, the norm of V, the Euclidean norm, on finite dimensional vectors. Euclidean norm is just the sum of the squares to the 1/2. Alex. It's an accident of the notation. Yeah. Well, there is. In discrete time, there kind of is. In a moment, I'm going to show you that L1 is a subset of L2 is a subset of L infinity. But, David.
I was just wondering that I get the raising it to the 1/2 creates like a parallel between this,
Mhm.
the vector.
Yeah.
But where does the 1/2 actually come from?
Okay, where does the one? That's a good question. For a norm, we want something like this to hold. We want, if I take a C0 times x norm, I want that to be equal to absolute value of C0 times the norm of x. Okay? If I don't have that square root there, what happens? Yeah. So the sum over n of C0 x of n squared is equal to that. So if I don't take the 1/2, so let's take the 1/2. That's why. Does that answer your question? All right. Okay, so now once again, just like for L1, in order for this series, this infinite series of squares of x of n, sum to converge, those numbers, those squares of x of n, have to constitute a bounded set of real numbers. So, observation, L2 is a subset, in fact a subspace of L infinity. So the same argument as for L1. And it turns out that L1 is a subset of L2, which in turn is a subspace of L infinity. And in fact, you can define the LP spaces, as they call them, for any p between 1 and infinity in the obvious way. Just the x of n to the p raised to the 1 over p. And in that sense, your idea about them being the limit is true. That L1 is contained in L2, is contained in L7, is contained in L 10 to the 59th plus epsilon. Yeah. All the way up to infinity. Now, to prove this containment is kind of subtle. What you do is you take an L1 signal and you separate it into a part where the things are bigger than 1 in magnitude and a part where the things are less than 1 in magnitude. And the part where they're bigger than 1 in magnitude, there's only finitely many of those. There may be infinitely many things where it's less than 1 in magnitude. The sum of the squares of those things are less than or equal to the sum of the thing. It goes like that. It's in the monograph. Now, this is really nice. It makes discrete time really clean in some ways. The continuous time isn't, because this actually does not hold when we do the continuous time analogs, no pun intended, of these discrete time things. Okay. So any question about these sets of signals? A lot of the time we're going to be encountering situations where we want to know if a certain set of signals is a subspace, whether it's closed under shifting, whatever. And these are sort of the primordial examples of such things. All right. So now what we want to do is we want to talk about another interesting operation you can perform on discrete time signals. We can take linear combos of them. We can shift them. I just want to make sure I'm not forgetting anything that I wanted to to mention in this context. So we're going to take this out for a second and have a look at my little... Yep. Okay, we are ready for the next interesting thing to do with discrete time signals. Because anyone want to hazard a guess at what that is? Convolution. Good job. All right. Now, we did some convolution in 2200, in my version of 2200, and I'm sure that those of you who took it from Professor Dorshuk or Professor Tong or whoever, you also did some convolution. But you didn't worry so much about all the details, like, you know, if you have two signals, when is their convolution well defined, that kind of thing. And part of that was because in 2200 you're dealing mostly with signals that start at time 0, and those turn out not to be a problem with convolution. But you'll see that when we deal with more general signals, issues arise. And it turns out that whether convolutions exist depend on whether things are in L1, L infinity, whatever. So anyway, we'll save that up. So the next topic is convolution of discrete time signals. And how does this go? Here's the definition. Given x1 and x2 in f to the z, the convolution of x1 and x2 and sometimes people say the convolution of x1 with x2 instead of and, whatever. I'm going to use those pieces of terminology interchangeably. If it exists, and that's a big if, and therefore rendered in all caps, is the signal and the notation we're going to be using for convolution is going to be x1 star x2. That's quite standard. With specification x1 star x2 of n equals the sum from k equals minus infinity to infinity x1 of k x2 of n minus k for all n in the integers. And once again, I'm trying to drive this home. x1 convolved with x2. That's the whole signal. Whereas x1 convolved with x2 of n is its value at time n. And this is so much better, in my opinion, than a notation like x1 of n convolved with x2 of n, which pervaded that book that we used in 2200, and also Tong used it. I don't think Dorshuk did, he might have. But in the book, it actually says at one point in the page, they're talking about h and x, it says this notation, h of n convolved with x of n, y of n equals h of n convolved with x of n, is bad. It says this is bad notation, but we use it. A better notation would be y of n equals h convolved with x of n. So we'll take them at their word. We won't use this notation. We'll use this notation. All right. So that's the definition of convolution. Now, clearly, existence is an issue. Because why? Because to figure out the value of the convolution of x1 and x2 at any given time, you have to sum an infinite series, right? And it's not a given that an arbitrary infinite series is going to converge. So that's why x1 convolved with x2 need not exist for particular x1s and x2s. And we have to look at restrictions that guarantee that existence. Okay, well, the first thing to note about convolution, so a couple things, a few sort of quote-unquote elementary properties of convolution. Are the following. First off, it doesn't matter where you put the k and where you put the n minus k in the definition. So it doesn't matter where k goes, where n minus k goes. And to be formal about it, if x1 convolved with x2 exists, then its value at time n, x1 convolved with x2 at time n, is equal to both the original def that puts the k with x1 and the n minus k with x2, and the same thing but with the n minus k inside the x1 and the k inside the x2. And that's true for all n. How do you show that? It's an easy change of index in the sum. Just let m equal n minus k. And in the monograph, we do that. And why do you care about that? Because depending on what the signals are, it might be easier to do one of those sums than the other, or at least it might feel that way. You know, it might feel that way to you because you're good at doing this kind of sum but not that kind of sum. But there is a conservation of hard work, yeah. Yeah, one can view it that way. One can, if you want to fancify this, as David suggests, you could say quote unquote, convolution is commutative. In other words, x1 convolved with x2 is the same as x2 convolved with x1. If you want to stick with that as being the definition, putting the k first, the n minus k second. And of course, we're going to have associative, distributive, and then we're going to have criteria for existence, but that'll have to wait till next week, I guess.